over the Chapter 21 applied questions. I'm making this video because you have, ideally, finished data set for your 5 generations of your population that have evolved. For this assessment, I'm going to be looking at how you developed and used models to show or predict relationships, ideally how your population evolved or didn't evolve over time due to factors in your model. In these two responses, your responses should contain clear, detailed examples of data that highlight major components of evolution and populations. You should cite numerical evidence from your data to make observations about your population, your model's rules, and how efficacious, how well they worked, how accurate they were, and how important those rules were. And then finally, you need to explain how your model's rules worked in terms of their parameters, their consequences on evolution, and also their limitations. Basically, did you design an experiment, a model that used different components of how populations evolve to either make your population evolve or not, using our evidence? So the first response is going to be, in your own words, explaining the rules and the model's requirements. Thinking about specific reasons as to either how natural selection, mate choice, or diverse and inheritable traits led to the evolution of your species. You could also and should also discuss the 5 components of Hardy-Weinberg equilibrium that you voided with these choices. You want to make sure that you cite numerical data points, which could be genotype frequencies, allele frequencies, and also the number of individuals that changed in a certain generation to talk about how these rules either worked or didn't work. Within your analysis, you might also consider the following points. How could you have made your model rules be more realistic or have been modified to make it stronger or weaker if you thought they weren't? 2, what other rules could you have added to have a stronger evolutionary pressure on your population or seen more changes? And then which of the factors, genetic drift, gene flow, or mate choice or environment, were the most prescient or the most important in your model, or using real life examples? See Chapter 21 for that. Which of your factors in your model was the most important for your population to evolve? Was it genetic drift, where allele frequencies change are more likely due to bottlenecking or founder's effect or population decline? Was it gene flow, immigration or emigration of genes, or mutation? Was it mate choice and sexual selection? Was it the environment? What caused your population to evolve? Below, we're going to do a chi-square test looking at your population. And to do this, you're going to be putting in row number or column number 1, the observed frequency of individuals that were PP, PQ, and QQ at the end of your population. This should be a percent, so maybe it's 0.3, 0.4, 0.3. Then you're going to be talking about your expected values. Your expected values are what we would expect to see if evolution didn't occur. This is a test that's looking to see if the null hypothesis, evolution did not occur, is true or not based on how the percent of individuals that are homozygous dominant, heterozygous recessive, and homozygous recessive changed over 5 generations. So maybe this is 0.2, 0.7, 0.1. Right off the bat, I know that these frequencies of genotypes are different, but also this is probably a disruptive selective pressure given that the PP and QQ genotypes increased. In the PQ, the heterozygous individual became less common. We're then going to look at our observed minus our expected and multiply it by 100. So 0.3 minus 0.2 is 0.1. Multiplied by 10 is 10. 0.4 minus 0.7 is negative 0.3, so it's a negative 30. And then finally, 0.3 minus 0.1 is 0.2 or 20, because we're multiplying by 20 to get whole numbers. We're then going to square our values. So 100, 900, and finally 400. I'm realizing right now that we want to make these also whole numbers. So I'm going to do that right now. So I'm going to get rid of this times 100. That is a mistake because the math is not going to work real good with that. So assume that your populations are out of 100. 30, 20, 40, 70. And the reason why is we were going to get really big numbers and that wasn't going to work. 30 and 10. So I'll put multiply by 100. And same with here. Multiply by 100. All right. Then we divide our observed and minus our expected squared by our expected to get the relative difference of the values. So 100 divided by 20 is 5. 900 divided by 70, oh, that's a fun number. 770, 840, 910, so it's going to be about 12.8. And then 400 divided by 10 is 40. And we add those values up. 5, 12, and 40. Notice the biggest relative difference here is the QQ. Even though 3 to 1 doesn't feel like our 30 to 10 isn't a big difference, it's really a tripling of the change. So this is our biggest relative difference. 40 to 70 is only decreasing it by about half, roughly. So this measurement isn't that big. 30 to 20, change of 10, but the relative value, the relative error isn't that big. So this is going to give me a value of 57.8, give or take. And then I go down here and I look at this chi-square test. The first thing to note is that we're going to be using 2 degrees of freedom. The reason why is if you are a PP individual, there are 2 ways in which you can show an unexpected change. You could create an offspring that's PQ or QQ. Now we know that a PP individual would have a really hard time mating with something to make a QQ. We're going to put that assumption aside. Right now the degrees of freedom are 2 because we assume that there's 2 ways to get unexpected values when we're looking at one individual. The thing that we're using for a critical value is 0.05. This is assuming that if our expected and observed are only 5% similar or 95% different, then the null hypothesis is not true. The alternative hypothesis is correct. And thus, when we look at 2 and 0.05, we get degrees of freedom of 5.991. That means that if the critical value of 5.991 is smaller than our calculated value here, then the null hypothesis is incorrect. And indeed, evolution has occurred. So for that, in your second response, did your population evolve significantly? There's a couple of different things that you can think of in terms of responding to this by citing data. Did you see directional, stabilizing, or disruptive selection pressures as a result of the changes that you saw between generation 1 and generation 5? Did in your model you see frequency dependent or sexual selection with how your phenotypes changed? Frequency dependent really means that the types of genotypes or traits in terms of their value is dependent upon the relative size and makeup of the population. So big antlers in deer may be or may not be a favorable trait based on what else is being presented in the population. And then sexual selection is just straight up one individual genotype is much more likely to get mates than the other. Furthermore, if you go to page 437, there's a couple bullet points about 4 as to why natural selection can never fashion a quote-unquote perfect organism. Populations and species are always evolving in flux to all of the things that we modeled. Environmental changes, population size changes, mutations, immigration, genetic drift, genetic flow. Based on those ideas, did any of the 4 bullet points that they talk about on page 47 meet the criteria of your model And does it show why we would never expect a population to actually achieve Hardy-Weinberg equilibrium, meaning evolution doesn't occur? In what ways do we see in our model a species never becoming perfect, never becoming still with natural selection and evolution? These responses are due on Friday. We can talk about them during class, but we are going to be beginning our chapter 22 work tomorrow. Let me know if you have any questions, and I look forward to reading your responses. Take care.